All right, we're going to go ahead and get started. Welcome, everyone. My name is Michael Kelly. I'm an application engineer here at Zoller, and we appreciate you joining us today for our basin sizing webinar. Before we get started, I just want to cover a few details. Please note the email address written at the bottom of your screen. Should you have any questions after we wrap up today or any feedback, you can send them to webinars@zoller.com, and we will get back to you. Now that those details are covered, I want to start off by telling you a little bit about myself. Again, my name is Michael Kelly. I've been working as Zoller's application engineer since February of 2018. I'm a certified engineer in training. I'm currently working towards my professional engineering license. I graduated from Western Kentucky University with a Bachelor of Science in Mechanical Engineering. And also while at Western Kentucky, I got my Master's in Business Administration. At Zoller, I work with customers, reps, and engineers with design and technical issues and applications including low pressure sewer, pump sizing, basin sizing, on-site wastewater, and other specialty applications. So now that you know a little bit more about me and my background, let's go ahead and get started with today's presentation. So today we're going to talk about the sizing and selection of large basin systems. In this presentation, you will learn some of the industry standards on how to properly size a wastewater or stormwater lift station. We're going to discuss why a properly sized lift station is important, as well as the various components to keep in mind when providing a turnkey solution for your customers. At the end, we're going to run through a quick example to kind of drive home what we talk about here today. So basins are everywhere in this industry. With very few exceptions, all the pumps produced by Zoller will go into either a tank or a basin of some sort. The primary purpose of that basin is to collect the water or wastewater in one common location, and that way we can place the pump there, then send it from point A to point B. So that's where they serve their primary purpose, but we want to be able to control the relationship between the volume of that basin to the output of the pump. Ensuring that there's sufficient volume for these pumps to routinely operate, we can ensure the longest life of the pump and the equipment for our customers. So just as a quick introduction on basins, it can have a different meaning for different people. Your typical plumber, your home builder, your contractor, this is going to be the particular basin that they see on a regular basis. This is for your sump applications, where if you've got a basement in an area where you get some heavy rainwater or high water tables where you might get some water in the basement, you'll have a sump pit very similar to this. We also have sewage basins that are similar to this as well. However, today, for the primary focus of our presentation, we're going to deal more on the larger side, which you'll see whenever you're dealing with municipalities, when you're dealing with large commercial developments where you have much higher flows, where they need a custom sized lift station. But again, to touch on the small basin packages, just to kind of cover these real quick. These are pre-engineered, pre-assembled, come in multiple configurations, and they can be used in many applications. If you go to your local wholesaler, distributor, you're likely going to find these on their shelves. The good thing about these is that they are pre-engineered. There's no more figuring. You don't need to size the basin. As long as the pump that comes in this assembly is sufficiently sized for the demand of the application, the basin will be fine as well. These are kind of the plug and play method. You just drop them in the hole, plumb them up, and plug them in. They're ready to go. They're that simple. They're that easy. And there's really nothing else that you have to do for these. However, again, what we're focusing on today is the larger basin packages. So we offer everything from partially engineered systems like our QLS system to fully customized prepackaged basin assemblies. For those of you who are not familiar with our QLS systems, these are fully fabricated lift stations with rails, discharges, and we can build and ship these in 3 to 5 days. So the lead times are very competitive. It's a very great option. If you haven't seen them, I suggest you reach out to your local rep or your distributor and ask them about this. But going off of that, we are frequently called upon to assist in the sizing, because one aspect of our QLS system and our other basin package systems, we have to ensure that they are properly sized. So the good news is basin sizing is actually very simple. There's just a few things to keep in mind to do it correctly, and we're going to discuss those things here today. First piece is that the basin should only be selected after the pumps are selected. So whenever I'm assisting with a project, whether it be for a municipality or commercial job, I always start with the pump and then we move to the basin because the necessary basin volume is figured from the pump runtime. And that pump runtime is based on actual flow, not just the design flow. So the question may arise, what's the difference between actual flow and design flow? So design flow is a theoretical calculated minimum requirement a pump must meet in an application. This is generally what we use to select the pump. This is, for those of you who are familiar with the fixture unit method, there's the population method. There's several methods out there that we can use to determine design flows. You can use existing water data. Maybe the local regulators have a set process for determining design flows, but that's the minimum requirement that our pumps need to meet. The actual flow, on the other hand, is the actual flow rate that the pump will produce. This is generally equal to or greater than the design flow. And for those of you who are more familiar with pump sizing, performance curves, and system head curves, the actual flow is where the pump curve and system head curve actually intersect. So as a quick example, we're not going to get into the weeds on pump sizing, but again, to just kind of drive home the difference between actual flow and design flow. Let's say we have an application where we need a flow of 50 gallons per minute. The static head is 18 feet and we have 4 feet of friction head. This gives us a design point of 50 gallons per minute at 22 feet of total dynamic head. That's our design flow for this. But let's say we've selected a 292 pump. Again, for those of you who are familiar with performance curves on a pump, the pump will only operate along that red curve. We can see that our design point is not on that red curve. So how do we know what the actual flow of this pump will be? That's where we get the advantage from the system head curve. The green line represents the system head curve. So now our actual flow or our operating point will be where both the red and green line intersect. The good news is, and again, we're not going to get into the weeds of pump sizing, but we have software on our websites where if you use your design point of 50 gallons per minute at 22 feet of head and also know what your static head is, it will tell you what your operating point, or I believe if you're on Zoller Pumps website, they call it the equilibrium point. And in this case, it would be 72 gallons per minute. So for basin sizing purposes, we're going to base our basin off of the 72 gallons per minute, not the 50 gallons per minute. So to understand it, we just need to understand the basic theory behind basin sizing. And there's 3 pieces to this. The first piece is make sure the pump or pumps fit, whether you're using simplex or duplex. You want to ensure that the pump will physically fit in there. And it's more than just making sure that there's enough room to fit 2 pumps in the bottom of that basin. There's rail systems, there's valves, there's piping, there's discharge assemblies. All of these things need to be factored in. There's also minimum spacing requirements that we need between pumps if we're doing a duplex system. And that's to ensure there's no negative interaction between the 2 pumps. And there's also some issues with cooling and so on. The good news is this has already all been figured out for you. Most manufacturers, including ourselves, we give this information. You can find it on our website. You can find it in our catalogs. You can find it by calling in. The second piece, after you've identified the minimum diameter, you need to factor in wasted spaces. So with any basin that we design, there's going to be areas of that basin that we cannot utilize for the storage or normal operating conditions of this basin. And those 2 are the minimum liquid level and the area above the inlet. The third piece is we need some minimum volume to ensure a reliable operation of the pumps that have been selected. And that's based on a 3-minute pump run cycle. So back to checking the physical fit. So again, the minimum basin diameter is based on pump drawing. So we have these drawings on our website, again, in our catalogs. If you can't find the particular pump you're looking for, call in and we'll get that information for you. But if you go to our website or looking in the catalog, you'll see a drawing that's similar to this one here. And you notice in the top right, you get a table. So for a simplex, which is one single pump, or a duplex, which is two pumps, you get two different diameters. So simplex for this particular pump model is a 36-inch minimum diameter basin. For a duplex, you have a 42-inch minimum. One important thing to note is that it's dependent on the pump family and the discharge size. So this picture right here is for our 651 or 600 series pumps. It's one of the larger pumps that we have in the Zoller pump line. You just want to make sure that you have the correct family. So if you're looking at a 53, for those of you who are familiar, that's our fractional horsepower sump pump. You could probably fit 4 or 5 of those in a 36-inch diameter basin. So make sure you have the correct pump family. The second piece is the discharge size. So the 600 series, the one in this picture, is available in several different discharges. We have both horizontal discharges and we have vertical discharges. Horizontal discharges usually take up a little bit more space and are going to require a larger minimum diameter. So you want to make sure that you have the right discharge orientation as well as the right discharge size. So we also have pumps that are available in 4-inch, we have some that are available in 6-inch, and so on. The other aspect of the wasted space is the minimum liquid level. So we want to leave some depth of water in the bottom of the basin. The depth, the primary purpose is to prevent drawing air. You also want to keep your pump submerged to help with the cooling. So whenever you're actually fitting floats or setting floats in the field, a lot of times we recommend just set your offload at the top of the pump. But the primary concern that we're worried about is drawing air. There's two issues that can arise for that. Airlock, it's a bit of a buzzword in the industry, but as kind of a brief explanation, that's where the water level drops below the inlet of the pump, allowing the volume of the pump to fill with air. If that air doesn't have a place to escape, the water will fill around the pump up into the basin, but it will not fill into the pump. So the water will rise, it will activate the pump, but as long as the air is still trapped in there, the impeller is just going to spin in air, and it's not going to move any water, and it's going to lead to an overflow situation. A lot of people will say, well, why not just drill in a weep hole? A weep hole will correct that issue, but weep holes can plug and so on. So it's best just to leave some minimum amount of water in the basin. The other issue with air getting into the pump is called air entrainment. So you can get air entrainment from vortexing, where a vortex forms on the surface and it pulls air into the intake of the pump. The other issue is where water is cascading from the inlet down to the water level. It could create air bubbles, which can get into the pump as well, which can be very damaging to the pump. It's very similar to cavitation. It will pitch your impeller, it'll tear up your shafts, and it'll tear up your seals. It also sounds similar. It sounds like you're pumping rocks. So leaving a minimum amount of water will help mitigate those issues. As a good general rule of thumb, allowing for 24 inches is usually safe on the basin sizing side of things. So always just account for at least 24 inches minimum. The other wasted space is the area above the inlet. So this is typically field installed. It's highlighted to the right with the green circle. Even though it's field installed, you can generally get a good idea of what level that may be. You may need to reach out to the engineer or the contractor or whoever it is that is designing or installing the system to get that depth. But usually at a minimum, it's going to be the frost depth. Now, if you're further away from the building, it could go a little bit deeper because you have to maintain your slope, your gravity slope out to the basin. But like I said, at a minimum, it's going to be at least the frost depth. If you're in the Northeast and the colder climates, it may be as much as 48 inches below the surface, or maybe even deeper. If you're down in the South where it's a little bit warmer, you're usually 24 inches is fine. But reach out, check your local codes, or reach out to whoever's designing the system and get that information if you can. Because what that does is it establishes the maximum water level in the basin. Therefore, any volume above that is considered wasted space. The primary reason for that is if water rises above that inlet, it's going to flow back into the inlet. And in severe cases, it may be enough so that it empties back into the building, coming up out of any floor drains or any showers or anything on the lowest level, and that's certainly something that you want to avoid at all costs. The other issue on a less severe case is if the water just rises above that inlet's going to fill with water. And that's going to slow down any water flowing into the basin because it's going to hit that wall of water at the end of the inlet. So any solids, tissues, or papers that may be being flushed down into this basin could potentially settle out in the inlet pipe and lead to a clog. So under normal conditions, you never want to go above the inlet. So we kind of established that as our maximum water level. So the working volume is the total usable volume in between those two wasted spaces. So in between our minimum liquid level and our inlet. Generally, we want a working volume equal to or greater than the amount of water pumped in 3 minutes. Now, one thing to keep in mind, our total working volume isn't necessarily our drawdown volume. Our drawdown volume, rather, is the distance between the offload and the lead float. So as the water rises, it's going to activate the offload, and then it'll eventually activate the lead float. That's going to send a signal to the control panel to activate the pump. So now the pump will activate and pump the water down to the offload. And that would be your typical drawdown volume. Again, we're not necessarily getting into exact float placements, but I just want to make that distinction between the total working volume and the drawdown volume. So in order to calculate the working volume, I've mentioned it a few times now, but we're going to use, again, the actual flow, what that pump will actually produce, multiplied by 3 minutes, and that'll give us our volume. So if we have a pump that produces 60 gallons per minute, multiply that by 3 minutes, we need a working volume of 180 gallons. One thing to note is that the letter Q is often used to represent flow in equations. So we're going to use the letter Q later in the equations that we share with you, but if you're ever dealing with an engineer contractor, you're trading emails with someone and you see Q equals this, just know that they're talking about flow, most likely for the pumps or flow coming into the basin. So it's good to understand what the working volume is, but the issue with that is we don't typically size or sell our basins in volume or in gallons. We typically sell them in inches of diameter and inches of depth. And the way we convert that is we just need to know what the gallons per inch is for each basin. So for each diameter basin, there's a set number of gallons in each inch of depth. As an example, a 48-inch diameter basin holds 7.83 gallons per inch. If you have 6 inches of depth, it holds 47 gallons, and it's as simple as taking that number and multiplying it by 6. A very useful thing to have, and we have included it as a handout for you all to download, is the volume per depth table. This is something that I keep by my desk. I recommend if you're going to be involved in sizing basins routinely, print this off, keep it in your notes, keep it next to your desk or wherever you can quickly reference it. This will allow you to pull that gallons per inch value rather quickly. You can see the center column there is our gallons per inch. So a 24-inch diameter basin has about 2 gallons per inch. If we double the diameter to a 48-inch diameter basin, we get about 7.83 gallons per inch. So you also know that you gain a lot of additional gallons per inch by going wider. So just going from a 24 to 48-inch diameter basin, we've doubled our diameter, but we've increased our capacity by 4. So that's an important factor to keep in mind as well. So I see a question. It says, why a 3-minute cycle time? Now, I guess this is a good time to make a note that this is a general approach to basin sizing. It's not going to fit every single regulation across the entire country. Now, the methods that we show here are kind of industry standards that will apply to 90% of basin sizings. 3 minutes is just, it's kind of a buffer. Typically, the distance between your on and off float needs to be around 1.5 times the pump flow, and that will prevent short cycling the pump in most applications. 3 minutes just gives us a little bit extra buffer for the additional alarm floats, the lag floats, and everything else. So to answer your questions, it's primarily just a rule of thumb, and it's an industry standard, and in 90% of applications is going to suffice for a sufficient basin size. Though I'll state it now, whenever you're submitting these, you need to make sure that they are to the standards of the local code or the local regulations. So that's a good question. Hopefully that answered your question. So back to this, the working height. So it's flow times 3 minutes, and then to convert that, that's our working volume. Is Q times 3 is our working volume. Then we divide that by the gallons per inch. That gives us our working height. Now, we always want a working height to be at least 18 inches. So why we want 18 inches is to provide sufficient vertical separation for our floats. We recommend a minimum of 4 to 6 inch separation between all of our floats, and 18 inches gives us enough room for an off float, an on float, lag float, and alarm float. So always make sure that your working height is at least 18 inches. So now to bring it all together into one simple equation, we get the total basin depth of the working height, which is represented by our flow times 3 minutes divided by gallons per inch. We get our invert depth, which is one of our wasted spaces that we need to account for, and then the 24 inches that we require as the minimum liquid level. So again, just to run through it and visualize it, the working height is the usable volume between the minimum liquid level and the inlet. You've got the depth to the inlet as your first wasted space, and then you've got the 24-inch minimum that we require at the bottom. So I mentioned this earlier, but it's important to remember that you can adjust the diameter. The process that we just ran through works really well, but if you're in a situation where you have a relatively small diameter basin but a high flow pump, it may force a very deep basin. Or there may be another issue where you're dealing with a lot of rock or whatever limiting conditions you may have that require you to go shallower. So remember that you can always go wider instead of going deeper. As a quick example, if we have a pump that does 140 gallons per minute, we want 420 gallons for the working volume. So the working height in a 36-inch diameter basin will be 96 inches or 8 feet. And we need to remember that that 8 feet of depth is only for the working volume. That doesn't include the 24 inches for the minimum liquid level, and it doesn't include the invert depth. So you're probably looking at a 14, maybe 15-foot deep basin for a 140 gallon per minute pump. Whereas if you go to the complete opposite side, 72-inch diameter basin, you only need 24 inches or 2 feet for your working height. So we can kind of see how going wider can shorten the depth of that basin. So that's just something to always keep in mind. And overall, that's it. That is the process. Like I said, it's very simple. It's very straightforward. If you can understand the 3 different pieces of that equation, you can size a reliable basin for the application. Again, though, I want to state again that you want to confirm with local codes and regulations on any additional stipulations that they may have. So we're going to go ahead and go forward with an example to kind of help drive home what we've talked about today. So we're going to start with an example here. We've got a turnkey sewage lift station, or we have a customer who wants a turnkey sewage lift station for a new large factory, including a cafeteria. No basin is detailed, but the specifications indicate duplex model 651s with standard semi-open impellers and a 3-inch MPT discharge. Provided design point is 200 gallons per minute, 30 feet of total dynamic head. The site plan shows the sewage inlet into the basin at a depth of 4 foot, and the same site plan shows an elevation difference of 21 feet. All that's great information. You will never get all that information on your first phone call, because likely if they're asking you to size the basin, they don't know what information you need. So if we go back to the kind of basin sizing theory, we can kind of begin to formulate what questions we need, because we need to make sure the pumps fit. So what pumps are we using? So we ask them what pumps we're using, or maybe we size the pump for them. Then we can find the minimum diameter. We need to factor in wasted spaces. Okay, well, what are our wasted spaces? The minimum liquid level we just assumed to be 24 inches. But the other wasted space is the area above the inlet. Well, how much area is above the inlet? So you go back and you ask them, how deep is your inlet. And then you need to determine the required working volume, which is based on a 3-minute pump run cycle. Okay, so we need to know what the actual flow is of this pump. So can you provide us what the operating point is, or can you provide us with enough information so that we can determine the operating point? So first step is identifying the minimum diameter. So we were given that this is duplex 651's 3-inch vertical discharge. So we'll go to the website, we'll go to our catalogs, and we'll find the 600 series pump with a 3-inch vertical discharge. This should be familiar because this is the same picture from earlier. And you'll notice that for a simplex system, it's a 36-inch minimum diameter. However, in this particular application, they're looking for a duplex system, so we will use the 42-inch as our minimum diameter. So what's the actual flow? So we were given the pump info that they're using duplex 651s. The design point was 200 gallons per minute, 30 feet of total dynamic head. So this is the performance curves for our 600 series sewage pumps. If we put our design point on these curves, we can see that the 651 highlighted in red will be able to meet or exceed that design point. But at the same time, the design point is not on the performance curve. So what will this pump actually do? And that's where if we go to our online sizing software, we're going to need our design point, and we're going to need the static head. So what's the static head? So we were given the elevation differences. They mentioned 21 feet between the inlet and the manhole. Now, most people will assume, well, our static head is 21 feet. Well, it's important to note that static head, your worst case static head, is going to be at your minimum liquid level to the outlet. So that's actually going to be down a little bit lower than that inlet. And for your standard basin, we don't know exactly what that is because we haven't sized the basin just yet. But for your standard basin, a good starting point is to assume 4 feet. If it turns out that your basin is much deeper than 4 feet or 4 feet below the inlet, then maybe you go back and recheck your calculations. But we'll start with 4 feet for a total static head of approximately 25 feet. So we were given the pump info, 651. We were given the design point of 200 gallons per minute, 30 feet, total dynamic head. We just calculated the static head. So if we go to our online sizing software, we could plug in this information. It will create a system head curve for us, and it will tell us that our actual flow in this situation is about 265 gallons per minute. And if you're not going to use the sizing software, you can also estimate this to some degree. You want to get it as close as possible. Sizing software makes it very easy. But even if you just drew a straight line through those 2 points, the intersection point would still be around 265, maybe 275 gallons per minute. So we would want to use that value. So as a quick equation review, again, we've got the working height in inches, which is our flow times 3 minutes divided by the gallons per inch, our invert depth in inches, and our minimum liquid level of 24 inches. So now all we need to do is plug in the information that we just got and calculated. So the working height. Again, our actual flow is 265 gallons per minute. Our gallons per inch for a 42-inch basin is 6 gallons per inch. That gives us a working height of 132 inches or 11 feet. So again, the working height does not account for the invert depth, and it does not account for the minimum liquid level. So 11 feet, once you add in the minimum liquid level and the inlet depth, you're probably pushing a 16, 17-foot basin. That's going to be a pretty deep basin. So why not go ahead and try a larger diameter just to check? So let's try a 60-inch basin. Again, the actual flow is 265 gallons per minute. Now, a 60-inch basin is only 18 inches wider, so the difference is, relatively minimum, but gallons per inch is more than double what it was for the 42-inch diameter basin. So now we get about 12.25 gallons per inch, and that will reduce our working height to 65 inches or 5.4 feet. Now, 5.4 feet for some people may seem relatively deep, but given the application, that's a pretty acceptable depth. So we'll move forward with the 60-inch diameter basin. So now that we know the working height, it's 65 inches, we just add in our inlet depth or invert depth. And again, it was given to us in 4 feet, but we want to make sure that we're adding the same units, inches to inches. So we'll convert the 4 feet to 48 inches, add in our minimum liquid level, which is 24 inches. That gives us a total basin depth of 137 inches. So the overall basin size is 60 inches in diameter by 138 inches tall. So it's important to note that our basin diameters are only in 6-inch increments. So if your basin depth isn't an exact multiple of 6, just go ahead and round up to the next value. I just got a question that isn't the flow rate too high for 3-inch diameter discharge pipe? One thing to keep in mind is this is the discharge of the pump. Now, generally inside the basin, the discharge inside the basin is the same as the discharge of the pump, but sometimes it can be larger. Routinely, we use our 1.25-inch grinders and we immediately step up to 2-inch. So just because the discharge of the pump is 3-inch doesn't necessarily mean your discharge piping will be 3-inch. Let me see here. I'm looking at my cheat sheets real quick. And yes, that is getting a little high. On quick glance, you're looking at about 10 feet per second in velocity. So maybe in this particular application, you'll use 4-inch discharge, but the pump itself being cast iron, we're not too worried about that high velocity through the discharge of the pipe or discharge of the pump. But yes, it would be good to go to 4-inch or maybe even 6-inch, depending on the length and the friction losses. Hopefully that answers your question. At this point, we'll open it up for any questions. We'll hang around for a few minutes. So if you all have any questions, feel free to let me know. Just glancing through some of the questions that have been asked. Someone asked, do you use different cycle times for different models of pump? What is the max start and stops per hour for Zoller pumps? Generally in the Zoller pump line, from the fractional horsepower up to 2 horsepower, we want 10 cycles per hour or less. So that's kind of your general rule of thumb. And that's kind of an industry standard. 2 horsepower or less is 10 cycles per hour. Now, if you get in the 2 to 10 horsepower range, they cut it down to 7 cycles per hour. And then 10 horsepower and beyond can be as low as 5 cycles per hour. So that is a very important factor in basin sizing. One thing I want to draw your attention to, though, is generally if you're getting above 2 horsepower pumps into 10 plus horsepower pumps, these are generally larger commercial or municipal applications. And in that case, they're almost always duplex. So if we have a duplex station with an alternating control panel, those pumps are sharing the load. So even if we can only limit our larger model pumps to 5 cycles per hour, if we have 2 pumps, now we can do 10 cycles per hour because pump 1 will come on, take cycle 1, pump 2 will do cycle 2, pump 3, or pump 1 back again will do cycle 3. So even if the system itself has 10 cycles per hour in a duplex application, each pump is only receiving 5 cycles per hour. Hopefully that answers your question as well. Someone asked, where are the downloads for this presentation? It should be, I believe, you have a little control panel off to the side, and there's a drop down that says handouts. You should be able to click on that, download it from there. Still going through some of the questions here. And if you can't find the handouts, again, email webinars@zoller.com. We'll get you any of the information that you need. Someone asked what the velocity guidelines are for pipe selection, and if at some point it's too much to switch from PVC, or if you need to go to maybe like a ductile iron pipe, or maybe go from schedule 40 to schedule 80. Generally, The minimum for this industry is 2 feet per second. For wastewater, the minimum is 2 feet per second. Now, I will advocate to increase that. I generally like to see a minimum of 3 feet per second. Primary reason behind that is we get more and more efficient with our water fixtures, with toilets, sinks, showers, to where our water content is going down, but our solids content is remaining the same. So the solids content is increasing. You know, a lot of people are shifting from a 2 foot per second minimum to a 3 foot per second minimum because, you know, the primary reason why we're worried about velocity is to keep those solids moving. If the solids increase, we need to move that water faster. So I generally like to see a minimum 3 feet per second. Now, once you get to a certain point, it can become too much. 8 feet per second is kind of where I draw the max at, because if you go above that, it could be damaging to your pipes, your fittings, and any of your valves. And that's kind of a standard for any type of discharge pipe, whether it be ductile iron pipe or it be PVC. Now, some do stand up against erosion a little bit better than others, but if you're getting into those higher velocities, I would recommend increasing the diameter of your pipe. I believe the sweet spot is about 3 to 5 feet per second, because the issue with really high velocities is you get really high friction losses. And unless you're dealing with a short run of pipe, you're going to have to increase your pipe size anyways. But kind of as a general rule of thumb, you kind of want to be in the 3 to 5 feet per second range. If you go slightly beyond that, it's not a major issue as long as you're not getting up to 8 or 10 feet per second. It says, how much, if any, extra volume do you add in to account for the tether length of a weighted float? Now, this, again, we're focusing on control floats. So there's pump floats and there's control floats. The primary difference is a control float is coupled with a control panel. A pump float or a pump control float controls the on and off position. That's a little bit different, and that can affect your sizing slightly, but what we're talking about here primarily is these larger lift stations where we'll almost always use a control float coupled with a control panel. And those are primarily, they're looking at a specific spot, a specific elevation, and usually about right where you tether it. These are narrow angle floats. So about right where you tether it is going to be that point at which it says, hey, there's water here or there's no water here. And usually you're looking at like a 4-inch tether length for these control floats. So in this case, there's really no additional adjustments that you need to make for your tether lengths. Someone mentioned, I couldn't understand how the static head counts in this case. The primary reason that we're only worried about the static head in this case was to determine the actual flow of the pump. So the static head has really nothing to do with actual basin sizing directly. What it does have something to do with is the system head curve that we would develop for this application. So if we know our design point, which was the 200 gallons per minute at 30 feet of total dynamic head in our example, and we know our static head, which was 25 feet, we can go to our pump sizing software available on our websites, and we can put that information in to get our actual design flow or our actual flow for the pump. And then that's the value that we use to size our basins. So that's kind of where the static head plays a part in this. So it's not directly tied to the basin sizing, but more so to the pump sizing, which then drives our basin sizing. Last question, where do I find the horsepower for the selected pump? You can go to our website and go to our catalog. It'll be available in our tech data sheets. You can call in and ask for it if you still can't find it. They do vary. To be honest, off the top of the head, I'm not exactly sure what a 651 horsepower rating is. But if you go to our website, it's all available there. It's also available in any of our catalogs as well. Let's see. I don't see any other questions coming in at this point. Hopefully I answered everyone's questions sufficiently. If for whatever reason you're still confused or you have additional questions, remember that you can also email webinars@zoller.com. We appreciate any feedback, any recommendations for future webinars, and so on. Make sure that you go ahead and download the handout, the volume per depth tables. Again, if for some reason you don't get it before we close out, or you have issues downloading it, again, you can email us to get that as well. But looks like no more questions are coming in. So I certainly appreciate everyone's time today, taking time out of their busy schedule to come educate themselves on our products and the various things that we need to keep in mind when selling our pumps. So I appreciate that from you all. But again, thank you for your time. Thank you everyone for joining us, and I hope that you have a good rest of your day.